Good afternoon, everyone. So let us wait for 5 more minutes and then we'll start the session. So, in the meantime, if there are any other students, they can join. Thank you. So, yeah, we can start now. I hope my screen is visible and all. And latest audio is unmuted. Yes. So, for your information, this video is being recorded. So, yeah, good afternoon, everyone. So, I am Anchor Kartika from the Department of Chemical Engineering, IIT Hyderabad. I am handling these live sessions. So, this is live session is being conducted to aid in problem solving for the assignments as well as the final exam for the NPTEL course Computational Fluid Dynamics. So the course instructor is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Madras. So all the lectures are covered by him. So these sessions that we have been conducting every week is just to help you in solving additional problems apart from the theory that is being incorporated in the lecture videos. So this session has been happening every Saturday from 3 p.m. to 5 p.m. and mostly we'll be having one more session next week, and it should be all for this, or at the max we can have 2 sessions, I'm not sure. So we'll be having one more session, and with that we'll be closing. So this is almost, we are like in week 11. So there was one additional lecture last day, that is yesterday we had one lecture on Friday. With that lecture we were discussing few problems from week 10 assignments and week 11 practice problems. So in today's class we'll be having 3 parts. The first one is nothing but we'll be solving few assignment related problems from week 11. After that we'll be solving assignment 10 answers, and then we'll be seeing week 12 practice problems. So that's the intro. So now let us move on to the session. So if we look at the course layout, we can see that we have been seeing too many things, and it is structured in a way that we got an idea of what is happening in CFD first, and followed by that we saw the governing equations, discretization schemes, and what we would be following, like a consistency, stability, all those checks that we would be putting at every step, we also check that. So that is our aim. So in that process, what we have seen is that in week 1 we saw about the calculation of flow in a rectangular duct, and week 2 we saw about it being done in the triangular duct. So we saw how to get the equations for the flow equations when we are using the rectangular and triangular duct, so that we were just able to say that this is how the calculation works. And for that means we did by using finite difference approach in the first week and finite volume method in the second week. So, and we saw the problems and we solved them in the these sessions. And in third week we saw about the derivation for equations governing fluid flow. As I said before, CFD is nothing but solving the governing equations and getting the solution. So the governing equations are nothing but the continuity equations and momentum conservation equations. So we should be having an idea of what we are doing when we say we are doing CFD thing. So it is like a part of computer fluid dynamics, where we visualize things that is happening inside the system through numerical methods and few models. Like we apply the numerical methods to the system, and we get the solution. So after that it was about equations for incompressible flows and boundary conditions, and then it was about basic concepts of CFD, like, and we saw finite difference approximations. like as we have discussed, there is like three commonly used techniques like finite difference approach, finite volume approach, and finite element method. So the discussion was mainly, all these lectures mainly govern the finite difference approach. And in week 6 it is about basic concepts of CFD by focusing on consistency, stability, and convergence. So when we are solving the equations through any numerical methods, we need to have an idea that we would be getting the solution perfectly, or we would be getting the solution converged. Sometimes it would be like solutions might be diverging, or solutions would not be stable. There would be so many errors and fluctuations. So we do not want that. So therefore what we do is we need to have some checks periodically from the equations that would say that we can have the consistent and stable and convergent solutions. So for that we also saw Lack's theorem and how it is stating the convergence theory and all. And week 7 it is about solution of Navier-Stokes equations for compressible flows. As I said before, like by solutions what we mean is that we mean that continuity equations and momentum conservation equations should be solved. So in continuity equations we have two things. Not in continuity equations. In momentum conservation equations, it can be for two-dimensional problems or it can be for three-dimensional problems. So basically on that we call that generalized form we have, and we need to get the solutions. So it can be compressible form or incompressible flow system. So the week 7 we were dealing with solution of Navier-Stokes equations for compressible flows, and later on we move to the incompressible flows. And in week 9 it is about the solution of linear algebraic equations by concerning the basic methods, and later on in week 10 we saw about advanced methods. So till now we have like almost covered everything, and now in week 11 the problem is regarding basics of finite volume method including grid generation, and later in week 12 we'll be seeing turbulent flows and turbulent modeling. So let us now look at the assignment problems for week 11. These are not the exact problems, these are just similar problems, so that on looking at it you will be having an idea how to solve the week 11 problems. So this is our domain. I guess week 11 assignment deadline is approaching, so please be careful and like try to solve maximum questions. And theory questions are there which can be easily solved when you people like if you listen to the lecture completely, you can solve the theory questions. And also if you have any doubts you can also follow some books. There are so many CFD books, and also there are so many reference books given as well, so you can follow any of that apart from the lecture series. That is what I am saying. So this is the figure 11.1. So this is sample triangulation of a semicircular two-dimensional domain. So this is a semicircular domain in which we need to solve for something. So we have done triangulation, triangular meshing is done, and this is a two-dimensional domain and it is a semicircle. So it is not properly done, it is just a sample triangulation. So on that basis we are going to deal with the questions. So in question 1 what we are going to deal, we'll read the question and then we'll answer. And before that I want to add something. I just want to insert page number because it is quite confusing for me as well. Yes. So now let us move on to question 1. In question 1 what we are going to see is that for the case shown in figure 11.1, which of the following statements is true? So we saw a semicircular domain with triangulation mesh, and which of the following statements are true? So first one, it is a structured grid. Second one, it is an unstructured grid. Third one, structured grid can also be used. Fourth one, unstructured grids can also be used. So we need to identify which is the grid. So for that we'll go back and look at the solution. So we can say that it is in form of some arrangement, but it is not a structured grid. Why we are saying that? Here what we saw in structured grid we saw that from one cell to the next cell, if we are identifying the neighbors, there should be some common ways of representing the neighbors. But here we can say that if I move in this direction, I am getting this neighbor, and like, okay, so like if I go from here to here, like sometimes, okay, here we can say that here to here and here, like I cannot identify the exact neighbors from the current cell, that is from the cell of my interest. I am not able to track the neighboring cell list. So I need to keep a track of a neighbor cell list. So I can say that it is the unstructured grid. But can we use structured grid as well? Yes, we can use structured grid as well. It would be somewhat complex than this to generate that sort of mesh, but it is generatable. So that is what I'm saying. It is an unstructured grid, and structured grids can also be used. So option A, 1, that it is a structured grid. Option B, 2, it is an unstructured grid. Option C, 1 and 4. And option D, it is 2 and 3. That is in option C, it is mentioning that it is structured grid, but unstructured grids can also be used. In option D, it is mentioning that it is an unstructured grid, but structured grids can also be used. So we all know that the figure showing is an unstructured grid, but we can also use structured grids. So right answer to this particular problem is option D. Okay, yeah. Now let us move on to question 2. In question 2, it is mentioned that given Dirichlet boundary condition along the curved side and Newman boundary condition along the diagonal of the domain shown in figure 11.1, how many algebraic equations do we need to solve simultaneously? So what is being asked? Yes, okay. We are given this particular geometry, and we are saying that along the curved side we are applying Dirichlet boundary condition. That is, we are applying the exact values all along the boundaries, and after that we are saying that Newman boundary condition is applied along this particular diagonal, and we are asked to find out how many algebraic equation needs to be solved. So we all know that it is an unstructured mesh, so we cannot go with finite difference approach. We need to go with finite volume method. So in finite volume method, we write the governing equations at each cell. So we do it for each cell. So in order to identify how many algebraic equations we need to be solving, we need to first count how many cells are there. So we'll just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 along the first row, and 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So 32 from first and second rows, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42. So and 42 along this row, and we have a small thing over here. So 44, 42 we can say that, and it would be like somewhat inclusive of those things as well in some case or not. It depends on the boundary condition which we are giving. So like this, since this is just parallel, it can be solved. That's what we are saying. So it is option A, 42 plus or minus 2. Option B, it is 32 plus or minus 2. Option C, fewer than 27. Option D, more than 25. So we have seen that there are completely 42 cells, and in addition to that we can say that 2 more cells are there from which we can get an equation or not. It depends on this boundary condition and the system. So we can say that it is 42 plus or minus 2. So that, like, we are just giving an upper and lower estimate for us, and we are saying that we need to be solving that many equations. So right answer to this particular problem is option A. If you have any questions, just ask. I don't know when did the meeting like I'm just sorry, like meeting ended without my consent. Just a minute, I'll just log in from some other account so that meeting won't end because of any other reasons. I'm just sorry guys, I didn't notice when the meeting ended. So as we have seen that in the last problem, it is 42 plus or minus 2. So now let us go on to question 3. In question 3, it is asked that which of the following statements is true about the solution scheme shown in figure 11.1. So what it is asking, which of the following statements is true about the solution schemes shown in figure 11.1. So in order to understand that, we need to first see what are all the options given. First one, local grid refinement is possible. Second, local grid coarsening is possible. Third, multi-grid approach is possible. And options are option A 1 and 2, option B 2 and 3, option C 1 and 3, option D 1, 2 and 3. So in the grid that is given for us, it is a triangulated mesh and it is an unstructured grid that we have seen. So now we must know whether we are able to get the local grid refinement or we cannot get local grid I mean whether we can refine or coarsen, that is whether we can locally change the grid size. Is that possible? Yes, it is possible because we have used the unstructured grid and it is as we have seen in the last class, that is yesterday's class, we have seen that in unstructured mesh when we are using that, we need not worry about locally refining at or coarsening, that is changing the grid density at one particular zone without us worrying about it in the other zone. That is, if we change the mesh density in one zone, it would not affect the mesh density in the other zone in unstructured mesh. So on that basis, we can say that local grid refinement is possible and also local grid coarsening is possible. So if it is possible, and also multi-grid approach is nothing but we are just using a series of grids to get the solution by reducing the errors. So we can say that all three are possible for our current system, because what is our current system? It is a semicircle In that semicircle grid, we have applied a Newman boundary condition and Dirichlet boundary condition along the diagonal and the semicircular walls, or vice versa, or whatever. And after that, we are having an unstructured mesh. Since we are having an unstructured mesh, it is possible to locally refine the cells, that is grids, or locally coarsen the grids. So on that basis, we can say that local grid refinement as well as local grid coarsening is possible. And then multi-grid approach is possible. Yes, multi-grid approach is also possible, because multi-grid approach is nothing but wherein we solve the solution by using a series of grids and thereby reducing the errors. So we can say that all three are possible. So on that basis, we are going with option D. Option D is the right answer. Now let us see question 4. In question 4, it is asked that which of the following statements is true about the solution of linearized algebraic equation resulting from the discretization of a steady scalar transport equation over the domain shown in figure 11.1. So whenever you are reading any question, just divide the question into parts, thereby completely understanding what is being asked in the question, so it will help us answer that. So what is asked, which of the following statements is true? So we are given a series of statements and we need to identify which of them is true. So first thing is we should identify with whether we are asked to identify the true statement or the false statement. And here we are identifying a true statement about getting a solution of the linearized algebraic equations resulting from the discretization of steady scalar transport equation over the domain. So we are having a semicircular domain, right? So in that domain, we are discretizing the steady scalar transport equation, and after that we will be getting a algebraic equations. So while solving that set of algebraic equations, what would be the case and what are the given statements that is true or that is false, we need to identify. So first one, SOR method can be used. Second one, ADI method can be used. Third one, LU decomposition can be used. And okay, SOR is nothing but successive over relaxation method, so which can be used in anywhere. Like it does not pose any restrictions in major cases. And second one is ADI scheme. ADI scheme is nothing but alternating direction implicit scheme. In ADI scheme, there is a criteria, I would say, or there is a restriction that it can be implied, that it can be imposed only when we are dealing with a certain matrix structure, like tridiagonal matrix structure. So only when those criteria are satisfied, we can use the ADI scheme. The third one is LU decomposition method can be used. Again, LU decomposition is a generic method which can be used anywhere. So I would say that 1 and 2, I mean 1 and 3 can be used, whereas 2 cannot be used because 2 is having certain restrictions in the form of tridiagonal matrix algorithm. So first one 1 and 2, second one 2 and 3, third one 1 and 3, that is option C is 1 and 3, option D is 1, 2 and 3. So I would say 1 and 3 are right on and on that basis I am going with option C. Finite volume approach is used to solve for the system in unstructured grid solution. Why have I okay? Finite volume approach is used to solve for the system in unstructured grid solutions. So for our case, it is an unstructured grids, and we are using finite volume approach. And successive over relaxation and LU decomposition methods can be used to solve the system, whereas alternating direction implicit method requires a condition for tridiagonal matrix algorithm to be met. Therefore, we cannot use the ADI method for the system. So SOR and LU can be used to solve the system, whereas ADI method, as we have discussed, requires a condition for tridiagonal matrix to be met, and we cannot therefore we cannot use this. So let us just see question 5. This question 5 is the last question for week 11. Similar problems, like this question 5 is for is having some similarity till question 5, that is question 1 to 5 is having similarity from assignments this week. So the question that is being asked is different in the context, but we can answer that if few people listen to this. So the question is, which of the following can be claimed as advantages of an unstructured grid method of solution over a structured grid solution? So why do we prefer unstructured grid over structured grid solution? That is what is being asked in this question. And for that reason, we should find advantages. Ease of tackling irregular geometries. Second one, ease of solution of Ax is equal to b after discretization. Ease of grid refinement after solution. So I'll just look at the options first. Option A 1 and 2, option B 2 1 and 3, option C 2 and 3, option D 1 2 and 3. So unstructured grid, why do we prefer it over structured grid? First one, unstructured grid has ease of tackling irregular geometries. That is true. I would say it is 1 and 3. Yeah. Okay. Ease of tackling irregular geometry. So when we are dealing with irregular geometries, it is not always possible to go with structured grid. If the structured grid is there, we can get a solution easily after discretization. So that is the advantage of structured grid. But we cannot always generate structured grid. That is a major disadvantage of structured grid. So in that case, we go for unstructured grids. And unstructured grids has the major advantage that we can use it to tackle irregular geometries, and further solution will be comparatively more complex than the structured ones, but it is like tackling irregular geometries is very feasible with unstructured grids, and then we can locally change the grid's density without worrying about how it would affect the other zones. So that is ease of grid refinement after solution is possible with structured grids. So I would say that 1 and 3 statements are right, which is rightly given by option B. So option B is the right answer. So yeah, now we are going to see week 10 assignment problems. That is this week 10's assignments problems we will be seeing and seeing the solution. So we have A, B, C, D, E, F, G, H. Why I am saying you can solve the assignments 11 if you look at it is that if you remember yesterday we have solved the week 10 problems that it was similar to this particular question, but the conditions and other things were different, but the overall thing was same. So therefore I would say that like you can solve week 11 as well if you look at it. Now let us look at the problems. Week 10. Okay, the problem statement. You wish to solve the steady state heat conduction equation in a two-dimensional domain as shown in figure 1. So we are going to solve for the steady state heat conduction. Rectangular domain EFGH has a constant source per unit area. Side AD has an adiabatic boundary conditions, while AB, BC, CD are convective heat transfer boundary conditions with H and T amp as the convective heat transfer coefficient and ambient temperature respectively. You use uniform mesh and use a second order accurate discretization of the governing Poisson equations. You wish to solve the resulting set of linear algebraic equations which you have expressed in matrix form as Px is equal to Q. So first, well, let us understand what is being given in the question. So we have a domain ABCD, and on looking at the picture itself, we can say that AD is an adiabatic boundary. So since it is given like this, it is just meaning that there is no mass transfer or heat transfer that is taking place across the wall. And after that, we have an inside wall EFGH, not wall, inside domain EFGH, which has a constant heat source per unit area. And AD is adiabatic boundary, and AB, BC, CD are convective heat transfer boundary conditions. So with H and T amp as convective heat transfer coefficients and T ambient temperature respectively. And we use uniform mesh and use a second order accurate discretization of the governing Poisson equations, and we will be solving the resulting set of linear algebraic equations which we have expressed in the matrix form as Px is equal to Q. For this problem, we need to answer the following questions. So here again, I would like to remind you again that we are solving Poisson equation. Poisson equation is nothing but OS square F. Since it is a two-dimensional domain, I am saying for two-dimensional domain. Dou square F by dou x square plus dou square F by dou y square is equal to C into x comma y. So, two-dimensional domain ABCD with a constant heat source per unit area over the region EFGH. AD has adiabatic boundary condition. AB, BC, CD has convective boundary heat transfer boundary conditions with H and T am as a convective heat transfer coefficient and T ambient temperature respectively. So that is what is given also. I'll just mention the equation so it would be easier. So this is the Poisson equation. I times, yeah. Into x comma y. Okay, so Poisson equation is nothing but dou square f by dou x square plus dou square f by dou y square is equal to c into x comma y. I should also mention in two dimension. If it is a Laplace equations, what we would be having? We would be having dimensional domain. We would be having additional z component. Then it would become dou square f by dou z square plus dou is equal to c into x comma function of x comma y comma z. That is the source term. And now let us look at the options given. So the question 1, it is about with reference to the problem statement, given there is uniform heat source over AIEFGH, you expect the maximum temperature on the plate to be. So here we are mentioning that EFGH has a uniform heat source over the area, and if that is the case, where the maximum temperature would be on the plate. At the center EFGH, inside EFGH but closer to side HG than EF, inside EFGH but closer to side EH than FG, outside EFGH. I haven't included the picture, I'll just go there and include it so that it will be helpful. You can close your eyes if you want. So these are the options. So first thing we should understand is that it has a adiabatic wall, and these sides are convective heat transfer coefficients, and heat is uniform over the surface, and like here convective heat transfer is taking place across the walls. So across the walls there is a transfer of heat, so we can say that it is dissipating the heat. So where heat would be maximum, that is temperature would be maximum. So at the center of EFGH, we cannot exactly say that to be at the center of EFGH. And next is outside EFGH. Again, outside EFGH is also not possible. So it must be either B or C. Why we are saying that EFGH is the heat source. So heat maximum temperature should be at the EFGH, somewhere along the EFGH. So it is not outside EFGH and it is not even at the center. Why? Because this is the adiabatic heat transfer. I mean adiabatic wall, there is no heat exchange. But rather DC and AB and BC, everything dissipates heat. So temperature would be lower along the, like it would be higher here and it is lower here. Higher here, lower here, higher here, lower here. and higher here, and it would not be lower over here. So we can say that it is inside of EFGH. Okay, not at the center. Just be careful, it is not at the center, but it is inside EFGH. Only we have the maximum temperature because we have the constant source over that region. We can say that EFGH inside is maximum temperature, but which side? So since EFGH and FG all are closer to the normal walls where convective heat transfer is taking place, temperature would be lower. But in EH side, what is happening? We have adiabatic wall, so there is no exchange of heat taking place. So we can say that towards EH it will be um, at the maximum temperature. So we can say that it is expect the maximum temperature on the plate to be inside EFGH but closer to side EH because here the adiabatic wall is there. So that is the reason to side EH than FG. So here it is closer to walls again. So it will be like dissipating heat compared to EH. So I would say that option is C. So yeah, we are right. The right answer is option C. Now let us go to question 2. In question 2, which of the following statements is true about side FG? So which is side FG? So this is side FG. Continuity of temperature across FG is sufficient to obtain temperature on it. Continuity of heat flux across FG is sufficient to obtain temperature on it. So I would say 1 and 2. I'll just check the answer. Yeah. So like what is happening is that we have FG at the bottom, right? EFGH. So along FG, which of the following statements is true? So first one is continuity of temperature across FG is sufficient to obtain temperature in it. So if we have continuity of the temperature, we can say that FG has this particular temperature. And similarly, if heat flux is there, that is much amount of heat transfer is taking place across unit area or something like that. Again, we can say that FG is sufficient. I mean, heat flux across FG is sufficient to obtain the temperature on it. So we can say that both 1 and 2 statements are right. So option A is the right answer. Guys, let us just take a 5 minutes break. I'm not feeling very good. It will not be even 5 minutes. I'll try to come back in less than 5 minutes. Yes, let us continue now. With reference to the problem statement, in the set of algebraic equations written as Px is equal to Q, the discretized Poisson equation. With reference to the problem statement in the set of algebraic equations written as Px is equal to Q of the discretized Poisson equation, which of the following statements is true about the matrix X containing temperature values at grid points. So here we are calculating the temperature. So T is the temperature at the grid points. And what would be P is the coefficient matrix and T is the temperature at the grid points, and constants would be coming in this another matrix. So as we have seen that if when we are discretizing the equation f along I and j vectors, so we will be having it moving from x to x1 to x2, y1 to y2, everything. So that coefficients we would take and put it in the P matrix, and those f values or in this contact T values we will put it in the x column vector. So x column vector here is the temperature column vector. So that's why we are saying which of the following statements is true about the matrix X containing the temperature values at grid points. So we need to again identify which of the following statements is true. First one, it includes temperature at grid nodes on sides AB. Second one, it includes temperature at grid nodes on side AD. And third, it includes temperature at grid nodes on side AFG. Fourth, A 1 only, B 2 only, C 1 and 3. For D 1, 2 and 3. So I would say it like all A, B, C, D. D must be the answer. Yes. Why? Because T is the grid point matrix, or T is the temperature value at all grid points. As you all know that after discretization of the equations, we put it in the matrix form, or Px is equal to Q. So in that, X is the temperature at all the grid points and P is the coefficient matrix. Px is equal to Q. Q is the constant values. So X is the temperature at all grid points. If it is at all grid points, it should include the temperature at grid nodes on side AB and side AD and side FG as well. So it is like literally including all the sides. So option D is the right answer. In question 4, with reference to the problem statement, which of the following methods can be used to solve Px is equal to Q from the above problem? Option A 1 ADI method, option 2 ILU method, Gauss elimination method. So we can say that 2 and 3 would be used. So let us look at the options. Option A 1 and 2, option B 1 and 3, option C 2 and 3, option D 1, 2 and 3. Okay, so I guess in this context we are able to use ADI method as well. We can just check if we are able to solve for the tridiagonal matrix algorithm, and then we can use the ADI method, that is alternating direction implicit method. This is question 5. In question 5, with reference to the problem statement, which of the following statements is true about the source term in the region EFGH? It strengthens the diagonal dominance of the discretized equation in the region. It weakens the diagonal dominance of the discretized equation in the region. 1 only, 2 only, 1 and 2. Neither 1 nor 2, one cannot say a priori. So this question we have seen in the last class itself. If EFGH is, which of the following statements is true about source term in the EFGH? So in EFGH domain, source term is constant. So if the source term is constant, that constant will be affecting the Q vector, Q column vector. Px is equal to Q. If the source term is constant, it would go and affect the Q column vector. There is no way it would be strengthening or weakening the diagonal dominance of the discretized equations. So we can say that the answer is neither 1 nor 2. Similar question we have seen in the last class also. So that is the answer. And in question 6, let us go on. In question 6, With reference to the problem statement, which of the following statements is true about applying SOR method for the solution of Px is equal to Q? First one, it is converged if it is between 0 and 2, where W is the SOR parameter. Second, its convergence rate is twice as much as that of Gauss-Seidel method. Option A 1 only, option B 2 only, option C 1 and 2, option D neither 1 nor 2. So we have a problem statement and which of the following is true about SOR method. So SOR is nothing but successive over relaxation method where omega is the factor. Omega, if it is between 0 and 2, we can say that it would converge. But apart from that, we cannot say that convergence rate is in any way linearly proportional to the omega value. And so first one is right, it is convergent if omega is between 0 and 2 and omega is the SOR parameter. And second, its convergence rate is twice as much that of Gauss-Seidel method, which we cannot say likely. So my answer is option A. Its convergence rate is twice as much as that of Gauss-Seidel method is the right. Is the false statement. Therefore, since we are asked to pick for the true statement, we are going with option 1. It is convergent if it is between 0 to 2, where omega is the SOR parameter. We will discuss question 7. In question 7, in comparison with the Gauss-Seidel method, number of floating point operations required for one iterative step of going from xk to xk plus 1th iteration using SOR method is. This question again we have seen in the last class, where we are moving from kth iteration to k plus 1th iteration using SOR method, and how can we compare the floating point operations between Gauss-Seidel and SOR method. So we can say that it is remaining the same between Gauss-Seidel and SOR method, where the number of operations, floating point operations required is same. Option A far more, option B twice as many, option C about the same, option D far fewer. So as we have discussed about this enough in the last class, we can say that it is about the same, because in Gauss-Seidel and SOR method, both the method remains the same apart from the inclusion of omega factor in the SOR method. Other than that, the calculation is remaining the same between both Gauss-Seidel and SOR. So there is no way which should be reducing or increasing the number of floating point operations happening in the SOR method than compared with the Gauss-Seidel method. So we can say that both are having the same floating point operations. So it is about the same. Option C is the right answer. Option D, ADI method for the solution of Ax is equal to B is based on the decomposition of matrix A into M plus N, problem into tridiagonal matrix, matrix A into LU, matrix, none of the above. So this question again we have seen very well in the last class. Matrix A is decomposed into two tridiagonal matrix problem. That is, the problem is being divided into two tridiagonal matrix problem. So option B is the right answer. Which of the following statements is true about the multigrid method of solving Px is equal to Q? It uses several grids for the same computational domain. It solves the same equations on all the grids. It uses the same boundary condition on all the grids. Option A 1 only, option B 1 and 2, option C 1 and 3, option D 2 and 3. So what is multigrid method? Multigrid method is nothing but where we are solving the system from final grid to the closest grid, so that we can reduce or dampen out the error caused due to fluctuations. So this reduction of error would further reduce the residual. So if residual is reduced, can say that we are getting a proper converged solution. So what we are doing, we are solving the system in a series of grids. So the first one, it uses several grids for the same computational domain. True. Second, it solves the same equation on all the grids. It is not true because we are dampening out the error in different grids. It would not be the same equation. Third, it uses same boundary condition on all the grids. So again, this is true because boundary conditions, however, remain the same. So 1 and 3 is the right answer. So I am suggesting option C is the right answer. So answer is option C. So thing now is, time now is 3:58. So I really want a break now. Let us take a 5 minutes break and then we'll come back and discuss the rest of the problems. Now let us start again. We will see question 10. In question 10, it is asked that the multigrid method is efficient in solving Ax is equal to b because equations are solved on the finest grid only at the end. Computation on coarser grid takes lesser computational time. Computation on coarser grids takes fewer iterations to converge. So again, we have seen this question in yesterday's class. So options are 1 and 2. Option B 2 and 3. Option C 1 and 3. Option D 1, 2 and 3. So first one is obviously wrong. So on that basis, we are discarding everything except 2. So second one is the only true statement. Why? Because we are starting with solving the solution in the final grid and then moving to further coarser grids, and then we'll come back at the end to the finest grid. But it doesn't mean that equations are solved on the finest grid only at the end. So we start and finish in the finest grids. So we say that equations are solved on the finest grid only at the end is a false statement, and apart from that, computations on coarser grids takes lesser computational time is a true. Why? Because in coarser grids, the information traveling will be faster than in the finer grids, so the calculations are less. Calculations are basically less because of the grid numbers. Therefore, we can say that computation on coarser grids takes lesser time. And third one, computation on coarser grids takes fewer iterations to solve because with further progress in the course's grid size, we have reduced or almost dampened so many errors. So in that basis, fewer iterations are only remaining. So therefore, we say computation on coarser grids takes fewer iterations to converge. So 2 and 3 are right. Question 11. Which of the following is true for an iterative solution? Rate of convergence is constant for a given method. Rate of convergence for a given method varies with grid size for a given domain of calculation. So first one, what it is mentioned, rate of convergence is constant for a given method. And second, it is asking rate of convergence for a given method varies with grid size for a given domain of calculation. I would say both are right. I'll just look at the answer and come back to the explanation. Okay. Convergence is constant. So the first one, rate of convergence is constant for a given method. Okay, what we are saying is that rate of convergence again depends on dt, dx, everything. So it again depends on the dx. So even though the method is the same, the rate of convergence would be depending on the grid size as well. So we cannot generally quantify the rate of convergence as a parameter for this particular method. That we cannot say this method gives the lesser rate of convergence or this method gives a higher rate of convergence. What we can say is that this method is for this particular meshing, it is giving higher rate of convergence, and this particular method for this grid size is giving lower rate of convergence. Like that we can say, but we cannot make it as a constant. So first one is a false statement, and second one, it is mentioning that rate of convergence for a given method varies with grid size for a given domain of calculation. So what it is saying, rate of convergence for a given method is varying with grid size for a given domain of calculation. So we have a certain domain, and rate of convergence for a given method is varying with grid size. So grid size varies from higher to smaller to smallest. Sorry, smaller to higher and highest. So with if grid size is small, there would be one rate of convergence, and if grid size is large, the rate of convergence would be different. So rate of convergence is depending on the grid size for this particular domain of calculation. So both, I mean not both, second statement option B is the right answer. So option A it is 1, option B it is 2, option C 1 and 2, option D neither 1 nor 2. So answer is option B, that is second statement is the right statement. Let us now go to question 12. In question 12, it is mentioning that which of the following methods require diagonal dominance for convergence? SOR, ADI, multigrid method. I think none of them. Options are 1 and 2, 2 and 3, 1 and 3, 1, 2 and 3. Okay, all, I mean not none, all three of them require diagonal dominance condition to be met. ADA is a tridiagonal matrix algorithm. SOR, successive over relaxation. Similar to Gauss-Seidel method, it also requires diagonal dominance condition for convergence. And third is multigrid method. Again, if it is there, it is best. So 1, 2 and 3 is the right answer. Option D is the right answer. Question 13. It is asked that under relaxation is used in which of the solution methods? Gauss-Seidel, multigrid. Options A 1, option B 2, option C neither, option D both. So you people can yourself answer this, that we are not using under relaxation factor in any of the methods, Gauss-Seidel or multigrid. Under relaxation is used in SOR method, where if it is between 0 and 1 we call it under relaxation. If it is between 1 and 2 we call it over relaxation. So neither is the right answer. So these are the questions from week 10 problems. So again now we have 50 minutes left and we have only 4 problems to solve, if I remember correctly. So those 4 are also practice problems from week 12. So that is based on turbulence modeling and everything. So let us just start and then finish, and then I can give you, I'll just recommend few things for CFD then. Yes. Which of these, first question, let us see, which of these is a characteristic features of turbulent flows? Chaotic fluid motion, high diffusivity, high frequency fluctuations. Option A 1, option B 1 and 2, option B 1 and 3, option D 1, 2 and 3, option B, option C, option D. Okay. So characteristic features of turbulent flows. What is turbulent flows? There is a so fast mixing taking place in the system that fluid pockets are traveling at a high velocity and there is a vigorous movement and there is like everything is happening very fast. So chaotic fluid motion. So there is no aligned or laminar motion, that it is a very random motion taking place, and we can say that it is a chaotic fluid motion. Second one, high diffusivity. Again, this is true because at faster rate of movement the information exchange is also higher, so we call higher diffusivity as well. And third one, it is high frequency fluctuations are higher in turbulent flows. So option D is the right answer. So turbulent flows are characterized by chaotic changes in pressure and flow velocity. Question 2. Time interval for time averaging of flow governing equations should be such that it is as large as possible. It should be much larger than the time period of the largest eddy. Option C, it should be much larger than the time period of the smallest eddy. Option D, it should be much smaller than the time period of the smallest eddy. Time interval for time averaging of flow governing equations should be. So, we are time averaging any problems, what should be the time interval for that? Like, first one, it is as large as possible. It is not the case because we are not going to have a large time interval for time averaging. Generally, we would be leaving out the initial and the towards the end conditions, and we would be taking in the middle. So, and then option B, it should be much larger than the time period of the largest eddy, or it should be larger than the time period of the smallest eddy, or it should be smaller than the time period of the smallest eddy. So answer should be B, because like we are time averaging things. So when we are doing time averaging of things, our ultimate aim is to have a system of solution where it is basically covering all the things that is happening inside the system. So for example, if you are taking a pipe flow, inlet is there, outlet is there. So initially when you are starting, you are giving the flow at the inlet. There is nothing inside the system. So initially it is starting to develop the flow and it is reaching the exit. and after that it is exiting, and towards the end also again what we have, it is like moving out, and at one point near the half of the column would be empty, and half of the pipe would be empty, and remaining would be slowly flowing out. It would be taking place in that way, right? So what do we mean by time averaging is that we do not want the initial thing that is happening and the final thing that is happening. So that is initial filling from inlet to outlet also we don't want, and final thing that is from inlet to outlet which is exiting. Or I can say that we do not mainly want to focus on the first particle that is entering from inlet, the time it is taking from inlet to the outlet, that is how much time it is taking to reach the outlet, that period we do not want for time averaging. Similarly, the last molecule that is going from inlet to outlet, that time period also we do not want, because once the inlet first particle is moving, before that there is nothing inside the system, so time averaging it would give us a wrong value. And similarly, when there is exit, the last particle is exiting, we do not want that as well, because after the last particle there is nothing inside the system, so system again becomes empty and it is giving a false values when we are doing time averaging. So we are neglecting those two things majorly, and we are taking in between things. So what should be the time interval? So should we take it as large as possible? There is no requirement for as such that, but that time interval that we are choosing should be covering all that we need. So consider the eddy formation. So smallest eddy is forming, largest eddies are forming. So if we want to capture the largest eddy formation we are using time interval, we need to have the time interval that should be larger than the largest eddy formation. Largest eddy formation obviously will take more time than the smallest eddy formation. So when we are doing time averaging, the time interval should be larger than the largest time period of the largest eddy. I hope it is clear. So our right answer is option B. We'll go to question 3. In question 3, mixing length varies with. So we say Prandtl mixing length when we are concerned with turbulence, mixing, everything. So what is mixing length? Does it vary with fluid viscosity, Reynolds number, normal distance from wall? Sorry, mixing length varies with option 1, fluid viscosity, option B, Reynolds number, option C, normal distance from wall. Option A 1, option B 2, option C 3, option D 2 and 3. So mixing length varies with Reynolds. 3 is sure. Yes. So mixing length is not varying with fluid property like fluid viscosity, nor it is varying with Reynolds number. Rather, it is focusing on the normal distance from the wall. So how much it is away from the wall. So that we call it as a mixing length. Prandtl's mixing length is the distance a fluid particle travels before it gets mixed with the surrounding fluid particles. So the distance it travels from that is a fluid particle, how much distance it is traveling before it gets mixed with the other particles, surrounding particles, is what we call it as a mixing length. In question 4, we are solving the case of a steady developing turbulent flow between two infinitely wide parallel plates using K-epsilon turbulence model. For this case, the number of differential equations that we need to solve is 5, 4, 3, 2. Okay. So the case we are solving is a steady developing turbulent flow between two infinitely wide parallel plates. So we are solving it between two infinitely wide parallel plates, and we are asked how many differential equations would we need to be solving. So I think it should be 5. Yes. So continuity equation we need to solve one, that is for sure. And again we have between two infinitely wide parallel plates, so we can consider it as a two-dimensional one. So momentum conservation equation in two dimensions, x and y or something. So right now we have three equations, and since it is mentioned that we are solving using the k epsilon turbulence model, we need to solve for one equation for k and one equation for epsilon. So we are getting two equations. So on the whole, how many equations do we have? We have one continuity equation, two momentum conservation equations, two turbulence equations. So total is 5. Answer is option A. So that's it for today's class. If there are any doubts, let me know, or else I'll give you some brief introduction on some other problems as well, because we have almost 40 minutes left. So we'll take a 5 minutes break, and if you have any doubts in that meantime, you can ask, or else we will discuss some interesting problems from CFD. So yeah, I think there are no questions. So I'll just give a brief idea. I just found out the computational fluid mechanics and heat transfer by Fletcher book. So I'll just give you guys if there are any good interesting problems. Mm. Okay, all problems are kind of big. So that's why I'm just searching for any interesting points. So what I am suggesting is that there is one computational fluid mechanics and heat transfer book by Fletcher, or I can say John C. Tannehill, Dale E. Anderson, and Richard H. Fletcher. So I saw a brief outline and it is almost covering whatever we have covered till now. So this is like a just giving out all things that we require for this syllabus. So the first it is about introduction, and there is a general remarks. After that there is comparison of experimental, theoretical and computational approaches, which we have seen in our class and the main course as well. So like there are three: experimental, theoretical and computational, which comes as a part of fluid dynamics. So in the modern fluid dynamics requires all these things to be necessary to get an idea on and work on different problems in fluid dynamics. So experimental approach is capable of being most realistic. Whatever results we are getting from the experimental things, that is the realistic thing that is happening in everywhere. And the disadvantages, but there are very huge disadvantages. Firstly, we need that setup. Imagine you're doing some simulations in a heat transfer thing, heat transfer equipment, and at that point, remember if to conduct the experiments you need that large set of experimental setup, but in simulation or in computation you can just simulate it in a computation if you have the required computational resources. And second one is scaling problem. You cannot imagine you are in a lab and you're doing some sort of problems and related to you're doing some study related to heat transfer in heat exchanger, and you are providing that data. Only with that data you cannot state anything if you to an industry. So you cannot say that this is happening in here. The same thing would be happening in the industrial scale that we cannot see in most of the times. We need to identify certain scale up values. So scaling problems is difficult and measurement is difficult. Like we cannot always measure all the data. Like imagine you are using a fluidized bed experiment, you're conducting experiments in fluidized bed. It is very difficult to track the particle velocity, but in computation you can just do it through computational resources. And again, operating costs, you need pumping power, and if it is like compressor, you need like those things, everything. Operating cost comes into picture, and equipment fabrication is also a issue when we are dealing with experimental setups. But to when we are avoiding experimental setups, we have theoretical physics, theoretical fluid dynamics, which is like general information from usually from first principle models, and it is giving clean general information, mostly in the form of formula. And but it is restricted to simple geometry, like we can say that cuvette flow everything, but it is simple geometry we can usually apply and get the data, and mostly for linear problems. But all these disadvantages are covered in computational domain, computational problems, computational approaches. There is no restriction in most cases, and complicated physics can also be treated. Time evaluation can be obtained of flow, time evaluation, not evaluation, evolution. Time evolution of flow can be obtained, that this profile is taking this much time to develop. For example, we say that we are getting a parabolic profile in the pipe flow problem, but in doing that experimentally we cannot observe when it is approaching that parabolic profile, but we can observe that from the computational fluid dynamics, where we can say that it is transitioning from the flow, and it is attaining a fully developed flow at this particular second. So we can say time, we can see time evolution of flow also. But there are certain disadvantages as well, like the truncation error, boundary condition problems, like computational cost is again an issue. And after that, this is about an introduction in the book, and after that we are dealing with partial differential equations. So we have seen in our case itself, like how we are classifying the PDEs, and like physical classification, equilibrium problems, everything we are doing classification. And then we are doing matching problems. And there is mathematical classification as well, like where we are classifying the partial differential equations into elliptic, parabolic, and hyperbolic. So those problems will have different method of solution. And then we see well posed problems, everything. Like these are the things that we have discussed in the class, and these are the things on which basis we got the problems. So I am just giving you a suggestion to read this book before the exam if you have time. And after that, it is about basics of discretization methods, where we are just dealing with truncation error, round off error, discretization error, consistency, stability, convergence. Everything is given apart from the introduction and finite difference introduction. And there are so many examples for obtaining finite difference equation using Taylor series, polynomial fitting, integral method, finite volume approach, and so irregular measures is also given. After that, application of numerical methods to selected model equations, like heat equation, wave equation, for everything we have applied the numerical methods to those models. And this is about part 1 in the book, and later on part 2, application of numerical methods to fluid mechanics and heat transfer, where we are dealing with the governing equations of fluid mechanics, like continuity equations, momentum conservation equation, energy equation if it is there, and species equation, and everything. After that, average equations for turbulent flows, boundary layer equations, turbulence modeling, Euler equations, everything. Like we will be covering the turbulence modeling in the next class as well. Like week 11 and 12, it is about solving for the turbulence modeling. And last, numerical methods for inviscid flow equations, boundary layer type equations, and everything. Later on in the final touch, we have numerical methods for Navier-Stokes equations. Here we have seen the compressible and incompressible method. In the book also it is covered. For compressible method, we have McCormack method, beam warming method, and other explicit and implicit methods are also given over that. So you can just have a look at it. And like after that, incompressible Navier-Stokes equation, and what is steam functions, stream function, vorticity approach, and other approaches are also given. And lastly, it is about grid generation, which we have seen today. So other things are like connectivity information, Delaunay triangulation, where Bauer algorithm, everything is mentioned. So apart from this, I would also like to give few ideas, not exactly ideas, few problems. Like I would just like to make few statements. I can say that. Uh, so yeah. When transformation of an unsteady scalar transport into something else happens, there is no mathematical change. Non-orthogonal form, there is no mathematical change from anything to anything, and there is no appearance of terms as well. Just the transformation happens. And secondly, we have ease of when we are dealing with unstructured grid method of solution. We have um, ease of tackling irregular geometries and ease of grid refinement after solution when we are dealing with unstructured mesh. And third, we have consistently evaluating of fluxes in infinite volume method means that flux conservation across the common phases of adjacent cells. And last, we have when we are dealing with Bauer-Watson algorithm for Delaunay triangulation method, they are inserted randomly. The nodes are inserted randomly. And what happens during advanced Freund method of triangulation is that triangles of high aspect ratio formation occurs. So like I would like to make few things clear that these sessions are just for aiding you in solving problems. So like similar problems are being given. So till this week it was lately given, but however this week and the next week the assignments similar problems are given earlier as well. So please utilize that and try to get more marks in like last two assignments, and you can revise. I mean these PDFs are available in the NPTEL, so please revise them before the exam, and also the solution for the assignments. This year's assignment is given in the NPTEL website as well. So they have posted the solution. So like before appearing for the exam, just make sure you have revised all the questions, and all the theory concepts also please revise. And like assignment problems and theory problems, if you have covered, you are like good to go for the exam. You can solve anything. If in addition you want to know, you can see the previous year assignment problems as well, which will be helpful for you. So previous year assignment problems are given in our class. Like here only we have been dealing with previous year assignment problems also, and so you can follow that. So like apart from my class, there is one more TA who is handling these sessions. He is handling on Tuesday, I guess. So if you people are not able to understand what I am saying, you can follow, I mean you can listen to his lectures as well. I mean you listen to his sessions as well, like where he or she will be solving the problems. So depending on your interest, you can do that as well. So like just to give you an idea. So that's it for today's class. So and then I'll just give you an overview. I'll just give you an overview before closing the session. So we have seen the assignment problems of week 11. Similar problems. So here we are asked to identify which of the statement is true. And in the previous picture itself, we have seen that it was an unstructured mesh, because we are not able to identify the neighbor cells from this with any means directly, rather than having a cell list. But it can be converted. This particular domain can be divided using structured mesh as well. So that is what is covered in question 1. And later we have seen how many algebraic equations do we need to solve. So since it is an unstructured mesh, we will be using finite volume approach. And when we are using finite volume approach, we are having 42 cells, like it would be based on number of cells. So we are having 42 cells, and so plus or minus 2. So later we moved on to 11.1, again since it is an unstructured mesh, we can do local coarse refinement or grid coarsening depending on our need. Why we can do, because it is an unstructured mesh, we need not worry about changing grid density at one region, that it would be affecting it. It would not be affecting in the unstructured mesh. If it is a structured mesh, we need to be worrying about that possibility as well. Multigrid is possible also. Question 4, linear as algebraic equation, SOI method, ADA method, LU decomposition. So we were saying that it is tridiagonal algorithm is not possible, and ease of tackling, ease of grid refinement is possible. Ease of solution after discretization in unstructured grid is not possible directly. So that's it for today's class. I just wanted to give an idea on week 11 and week 10 problems. Here we have seen similar to yesterday's problems. So in week 12 also we have seen the practice problems, non-graded assignment problems, where we have dealt with turbulent flows, and it means that it has chaotic fluid motion, high diffusivity, high frequency fluctuations, and time intervals it should be larger than the time period of the largest steady formation, and mixing length varies with normal distance from wall, where we say Prandtl's mixing length as the distance a fluid particle travels before it gets mixed with the surrounding particles. Fourth one, it is about how many number of equations. Since we are considering it as a two-dimensional domain, we have one continuity equation, two moment of conservation equation, three equations, and along with that we have k and epsilon equation as well. Since we are using k epsilon turbulence model, we have two more equations. So on the whole we have 5 equations. So that's it guys. I thank everyone for attending today's sessions. We will meet again next week Saturday, unless until it is priorly informed. If there are any changes, it will be priorly informed to you guys. If not, we'll be having at the same time. So yeah, thank you. We'll see again next week. I'll be here for 5 more minutes. If there are any doubts, please let me know. That's it guys for today's class. We have 15 more minutes. So for that reason, I'll be staying here for 5 more minutes. If you have any doubts, you can ask, or else I'll close the session. Thank you.